Good evening to you all. This is Meta Tender Divine from group SWAI9, and this is our project. It's called Knowledge Graph-Based Spatial Temporal Intelligence for Real-Time Campus Crowd Detection and Recommendation. This project has the following keywords, as you can see on the slide: knowledge graph, spatial temporal modeling, campus crowd management, graph neural networks, fairness, aware recommender systems, and privacy preserving geolocation analytics. And those below are my group members. Then on the next slide, it contains the content for the presentation, the introduction, the problem statement, research questions, and so on and so forth, as you're going to see in the next slides. So for the introduction, we are going to talk about the problem, our solution, and the key technologies involved in this project. The problem is crowding at around campus locations like libraries, cafeterias, which may harm students' experience, efficiency, and safety, such as theft, and also their time around campus. Then our solution is a real-time system to detect and predict and manage the crowds on campus using spatial temporal intelligence. And our key technologies are the campus crowd management, and here the goal is to optimize campus flow and resource usage. Then also spatial temporal modeling, understanding how crowds move through space and time. Space is basically location, and time is basically the time series, let's say lunchtime, breakfast, morning, things like that. Then knowledge graphs, these are like smart maps that connect locations with contexts like class schedules and events. Let's say if the exam time, how does the crowd change during those such times. Then we have graph neural networks, which these are the brain of AI, which learns from the cages, the knowledge graphs, to predict future crowd levels. Then we have the fairness aware recommenders. This is an engine that suggests alternatives without creating new bottlenecks, whereby it helps us to be able to manage the crowds and balance them without creating new crowds that are really extra. So then we have the privacy preserving analytics. This analyzes the crowd data ethically and also anonymizes it. So on this slide, we are going to talk about the related works. Those are the papers that were investigating crowds and finding a way to manage crowds, and the models they use, the results, the architectural limitations, and the context limitations. The first paper was one of the first papers we picked out was crowd forecasting using Wi-Fi sensors, which used the LSTM model, the long short-term memory neural networks, which were able to achieve high forecasting of crowd counts based on those Wi-Fi sensors, and the model processes data as independent time series. It fails to capture the spatial relationships, the location differences, like that. Then the limitation was it was only predicting and it wasn't offering recommendations for other spaces. Then the other paper was crowd counting and density estimation using deep networks. This one used the CNNs, which are the convolutional neural networks that were successful in estimating crowd density heat maps. It used camera feeds only. Yes, and the structure, the architectural limitation is that this structure was not suited for modeling complex and non-uniform layouts like campuses, where I find that not all places have cameras, and the contextual limitations was it relied heavily on camera infrastructure everywhere. They only used cameras. And then as other papers like the 2019 TIS Temporograph Convolution Network for traffic prediction, it used the GCNs, the Graph Convolution Network, and the GRUs, the Gated Recurrent Units. These were effectively predicted traffic, yes, speed on a road network graph, and so on and so forth. The architectural limitations, the contextual limitations, as you can see, even This next slide continues with two more papers that we picked out, and then let me end the slide with our project contribution. So our project contribution is going to use knowledge graphs together with temporal graph neural networks and a fairness constrained recommender system, and our aim is to be able to predict density forecasts fairly, give fair contextual area recommendations for the entire campus. And the architectural limitations, I would say it integrates a multi-relational knowledge graph to fuse the diverse data sources like Wi-Fi logs, events, weather, using IoT sensors, and also geolocations. And to overcome this limitations of the simpler graphs that we have seen in other papers, as you would read through, then it's explicitly designed for campus context only. That's its contextual limitation. Yes, it will only serve for campus, not for like the whole really region or something. Then to continue on the next slide, we have our problem statements, and we have the domain problem and the computational problem. The domain problems, these are basically real world challenges, inefficient resource allocation, whereby the administration doesn't have enough real-time data needed to dynamically allocate or open up service areas. So we have degraded students experience, whereby students may be wasting a lot of time on queues, maybe taking lunch for long. Their study experience may not be good. Then we have on campus, we find that the management of these crowds is reactive more than proactive. Like, they often react to the crowds after they have occurred, but for us to want to bring something new by preventing it. And then the computational problems, these are basically the technical challenges, where like heterogeneous data that is different, Wi-Fi, IoT sensors, event schedules, and you find that it's noisy, inaccurate, like the inaccurate GPS locations. You find that it is incomplete, like sensor readings may be missing, it's irregular, non-uniform. Yes. And then we have also the context and stated relationships. You may find that there are some crowd behaviors that are not really so explicitly stated, whereby you may find that a student may be getting out of one lecture and wanting to go to a nearby cafe to have something to eat. Then we continue to the next slide, which is our research questions and objectives. And our research questions are basically, how can we best model this in a complex campus environment? How can we accurately be able to predict these crowds using our model? And how can we be able to fairly generate recommendations to actively balance these crowds? And how can the system work in real time while ensuring that data is privately kept? Yes, and our research objectives were to develop a comprehensive campus knowledge graph that models facilities, pathways, events, and other contextual factors, to design and implement the temporal graph neural networks model, a model that performs crowd density forecasting by reasoning over knowledge graph, and to create fairness-aware recommendation algorithms that suggest alternative routes and be able to balance crowd distributions around campus. Then to also generate privacy-preserving analytics into our data collection, so that data collection and model pipeline. Then our research contributions and outputs, we were able to develop a new architecture that combines knowledge graphs and graph neural networks for context-aware crowd modeling. And we built an innovative recommendation engine designed specifically for balancing crowds in physical spaces with fairness. And we're able to develop an end-to-end application design that is practical, scalable, and built on a foundation of user privacy. We are creating a new valuable anonymized campus mobility dataset, and a new class of analytics to empower data-driven university administration. Yes, and to continue, this is our methodology, like the system architecture, where we are going to collect the following data: Wi-Fi log, access logs, mobile geolocation, IoT sensors, data events, schedules, to feed into the knowledge graphs, and then the knowledge graphs to be able to feed into the temporal graph neural networks model, and then be able to give a fair recommendation through applications like phones and for administration and students. Then our model architectures, the models we try to pick out to be able to test on our data sets that we are able to choose. We have this one, which takes in the time series data, spatial data, and metadata into the knowledge graph that's constructed. And this data, the knowledge graphs have vertices and edges, whereby the vertices are the nodes or the facilities in the case of campus, and then the edges are the relationships between these facilities. Then, yes, as I was told, and those are different. So the knowledge graph feeds into the graph neural network, and then there's reasons over this. We have two models that we use here. We use the spatial temporal GCN, graph convolution network, and the GNN. So the spatial temporal graph convolution network is the primary model, and then this one is just a backup or a support, because for it doesn't take in the time series data, it only takes in spatial data. So after feeding in the knowledge graph, they are able to fuse the collected from the different layers, the collected predictions from the different models, and then give a fair decision, crowd prediction, recommendation, or alerts. Yes, and those are the different formulas, that explanation of the previous architecture for our first model. So this next model combines a GRU, OTCN, and a GAD. And those are the different layers it has to deliver up to the fair recommendations. Then those are the different formulas that it uses to be able to achieve what it has to achieve. Then the other model is the relational graph convolution network, that it works together with the GAT, the graph attention network, to be able to also produce the recommendations together with also the temporal convolution network. As you see the different layers and the different formulas that are being used, then it forms that is a hybrid model. Then our data set had 207,315 rows and 10 columns that we used to display some of the rows. That's how some of our data looks like. Then the different graphs we use to analyze the data. As you can see, the methods we use, the objective behind this analysis, and the insight we are able to derive. Also this other one, the label distribution, we are able to assess how the labels were in our data. So those are the methods we use, the insights. Yes. And then the second one, also the entity type frequency, where we use the horizontal bar plot. Yes, as you can see. Then the correlation, the different correlations we have been explained in the slides, as you can see there. We also have the still explaining the correlation matrix. Then data cleaning. This is our data cleaning process. Now we replaced all the null values in acceleration that were around 60,000 with the mean acceleration, and this is how we split our data to train our models. It was a 70 for training, a 15 for validation, and a 15 for testing. Yes. And so these are the results we got from the first model, the SGCN, and together with the GAT, the assembled model. Those are the results. We use precision, recall, F1 score, accuracy, AUC, and those are classification matrices that we used: training results, validation results, and test results, as you can see. And also then this model, these ones use the regression matrices to assess the performance of the model, as you can see also here. Then here, this is the model that was selected, and this is architecture, and these are the reasons: because it combines both spatio-temporal dynamics, yes, and then it was extended with a GNN for spatial interpolation, or as an ensemble. Then that's how our interface looks like for the for the product that we have developed. Then this is the user experience interface. You have the user experience, you have the admin experience. These are the interfaces we have so far, and those are the IP assets that we have, our data set that we're collecting, the security mechanisms, and the system architecture. Then the limitations is that GPS is normally, locations are normally noisy, yes, and the rest of the limitations. And the other side has the suggestions for those limitations, and also the conclusion, yes, what we're able to implement and how it's going to be used, and the future works, what we hope to improve in the future. Yes, and those are our references that we used, that basically picked from the papers that we discussed in our related works. And I would like to extend my sincere gratitude to our Department of Networks, in which my course is software engineering, for providing the academic framework and resources for this project, and special thanks to our supervisor, Mr. Galewango Marvin, for his valuable guidance and support and insightful feedback throughout the project. Thank you.